but it will definitely be something that's relevant to exam number 2. We're going to, well, we just did session 8, all right? So we won't do the recap, but we're going to talk about torsion on a shaft. And if you remember from the early days, okay, let's get through this. Okay, yeah, those are some review things if you're interested. Okay. All right. I don't have it here. Okay, but the early days, okay, in the early days, we said there were essentially 3 primary structures plus 1. We had bars, okay. We had shafts, okay, and we have beams. Okay. So we have graduated from bars and normal loading, and we're going to now focus on shafts. Okay? And then we'll spend a lot of time on beams, and then we'll do some other, well actually we'll do some stuff in between, and then we'll go back to the beams. All right? Beams are important. Shafts are important too. Okay. There are also trusses, right? But trusses, you have to endure my bad drawings here, that's all. You know, trusses are forms of bars. We're not going to have much in the way of shear stresses in them. At least we hope not. Okay. So by the end of this, all right, the idea is that we should be able to know something about maximum shear stress experienced at the outer surface of a circular shaft. We should know something about shear strain at a distance away from the center line of a circular shaft. Yeah, not really. Okay, we're not really going to talk much about the normal stress. Okay, although if I have a shaft and I apply stresses or forces at the ends, that's the normal stress. But that's not really what we're talking about here. Okay, we should be able to talk about shear stress at a distance away from the center line of a circular shaft. We should also be able to think about a maximum shear strain at the outer surface of a circular shaft. Okay, so those are some of the things that we should cover in the next 20 minutes or so. Shear strain. All right. This is often induced by what we consider to be sliding. So we talked about shear strain a little bit previously, but I glossed over it quite a bit. Now we cannot ignore the truth of shear strain. Okay? So remember, we have some element and we have a dx and a dy. If we then take this element and we move the top over, okay, we get this kind of deformation, right, where the 90-degree angles that we had in our nice square profile are no longer 90 degrees. And we know that we slid over by this amount delta, right, here and here. And now we're interested in the angle right where I have my mouse. Okay, and there's a blow up. And that is what we call the shear strain. And it's usually a small angle. So even though you can see like delta over dy, right, is the tangent of it, eventually we say that gamma is just equal to delta over dy, approximately. And just like we talked about equilibrium with tau xy is equal to tau yx, or sorry, well, I said it, right? Yeah, tau xy is equal to tau yx. We get to similar situations where gamma xy is going to be equal to gamma yx. Okay? So whether you think about the shear strain coming kind of out of a, like, because here why am I saying this? Because if I think about this, I would say, oh, there's some type of, like, since this is displacing this way, I could think about some type of shear strain that is coming out of the y surface, right, and going in the x direction. Okay, but that's the same thing, but it's the same thing as thinking about coming out of the like an x surface, right, and going in the y direction. Okay, so that's gamma xy. Okay, so there's a Hooke's law for shear stress and shear strain. Remember, Hooke's law for normal stress was sigma equals E. All right, epsilon. Here, I don't know what you can say, but actually I do. I say tau equals go. All right, that's Hooke's law here. G times gamma, or G times gamma. All right. So that's actually maybe tau is equal to G. I don't know. G. All right. Because it's two G's. So just like we plotted stress strain plots with sigma versus epsilon, you can plot shear stress versus shear strain, which is what you have here. And if you have a ductile material, then it's going to come over a little bit further. On the element itself, okay, this deformation, this gamma, like we said, gamma xy, is often associated with a shear stress. So the shear stresses end up being drawn as arrows like these, okay, whereas the shear strain ends up being drawn as angle like that. Okay. Yes, they're related to each other by 90 degrees. Okay, but actually, it's okay. So I'm telling a half truth here. In reality, when you start looking at some of these things, and it's not so important for this class, what we actually end up looking at are things that look kind of like this. They kind of go like this. Okay, this is because this is essentially constraining this thing down to the bottom surface. Okay, but anyway, and so often what you're going to see is this is like gamma over 2, and this is gamma over 2. So when you take a graduate class in mechanics, all right, they're going to talk about shear strains this way. But anyway, torsion of a shaft. Now you're like, what does that have to do with what we just talked about? Well, let's think about it. Forget shear strain. Forget shear stress now. Imagine I have a cylinder. Okay? And I have a bunch of pizza slices on it. And this is, if you come and visit me in the office, this is the table. Right? And this is your Yolanda's pizza. I made an excuse. It's like, I need a demo, and I'm going to go buy a slice of pizza. All right. So this is a slice. You see, this is a slice along the cylinder. Okay. And then I've got a slice on the slice. You see this? This is like this width of the table is each one of these different pizzas. All right. And this little slice of the pizza, although it's not proportional to, you get the idea, right? This is a slice on that pizza. So I've got a bunch of pizzas stacked, and then I've got a pizza slice here in the middle of the bar. Is that picture kind of clear? Okay, so, or I've got a slice of pizza here on the end. Okay. If we now have done a lot of spring work, right, with elongation. Now what we're talking about is rotational work. Right? If I apply a moment, so this moment is coming out of the face X, right? So right hand roll, it's twisting it this way, which means that the longer this bar is, the longer the shaft is, right, the more rotation you're going to have for a given amount of torque. Does that make sense? Right? It's like if I take a long branch and I start twisting it, right, I can deform it a whole lot more. If I cut that branch in half and I put the same amount of torque on it, it's not going to my hands are not going to rotate as much relative to each other. Okay? So we begin to see that this angle of rotation, okay, this alpha or this phi, all right, is going to be proportional to the length. Right? And that the phi, the angle of rotation, or the angle that my pizza slice carves out, is going to be dependent on how far along I am on this shaft. So if I'm halfway along the shaft, if I'm at L over 2, that angle of rotation is going to be half the rotation at the end. Does that make sense? Okay. This is just using our experience in the world. We've twisted things. Okay. So now, how in the world does that relate to something that we've been talking about? So now we're going to try to merge shear strain with a shaft. Okay, bear with me, and I'm going to use the mouse for this. So this is from Crandall, Dahl, and Lardner. This is the book that I used when I was taking mechanics. All right, and I think I probably have the last edition because these very well-esteemed authors, I believe they may have all passed by now. Okay, but anyway, so this I think I had the last edition of their book. I think there were only 2 editions, but anyway. So here is a portion. This is the pizza. All right, this whole thing. This delta Z is one of the pizzas that I've stacked in my cylinder. All right. And now, maybe this is, you can consider this to be the crust, all right? Like, you see there's this like shady line and this green line, okay? So this is some annulus that I've just drawn on that's smaller in diameter than the green circle, okay? But it's solid. It's not hollow. It's a solid piece, okay? Now, rho is the distance from the center to whatever circle I draw on this pizza slice. Okay? This overall radius of my pizza is called C. And C is a pretty standard parameter. You're going to see. Yes, you'll see the C. Okay? Rho is also a pretty standard parameter. Okay? Now, let's just say in the untwisted state, when I have not applied any torsion, I've now drawn A, D, H, E. Okay? Why not C? Because C, for some reason, defines the radius. All right? That's why that's why we have different letters. And this is coming from CDL. All right? Now, and if you remember your polar coordinates, maybe you get excited. Okay, we can have an R coordinate, we can have a theta coordinate, and we can have a Z coordinate. Okay, this is if you want to do that. All right. Now, what happens? We twist. All right. We apply a torque, a TZ. All right. So this was the untwisted state. Now this is this torqued state. All right. And now we go back to looking at pizzas, slices of pizza. Okay? So imagine this is pizza slice, I don't know, here or here, whatever it is. The whole pizza has rotated some amount phi. You get that, right? The whole pizza, or the bottom of the pizza, has rotated some amount phi. Okay? That bottom of the pizza is over here, like maybe it's on this part, and the top of the pizza is over here. The bottom of the pizza, I'm twisting this direction. The bottom of the pizza has twisted because of everything before it. It's twisted some amount phi. What's happened to the top of the pizza? Well, the top of the pizza twists a little bit more. All right? So like twist and shout. I don't know. It's shouting and twisting a little bit more. All right. So we've got, so you see this. This was the original D, DH. Now D has come over to D1. H has come over to H1. Up here, we had an A and an E. All right. So this is now A naught, we'll call it. E naught. All right. Because that, we're saying that's where it would have been if it had just followed the bottom of the pizza. But it didn't follow the bottom of the pizza. Because it has some thickness to it, it twisted a little bit more. All right. It's twisting and shouting a little bit more. Come on, come on, come on. All right. So now we've got this A1 over here, this E1 over here, right? So A is like all the way over here, A1, E is all the way over here. You can see, all right? And in this little slice of pizza, all right, right there, we have a delta phi. All right, so we had a phi describing how much the whole pizza had rotated, and the top has rotated just a little bit more than the bottom, and that's delta phi. All right, so this delta phi is going to be the same, right? I mean, it's an angle, right? So if I'm at E naught E1, or if I'm at A naught A1, wherever I am, that angle is the same. Okay. If I want to know the distance, all right, and this is, you know, the essentially of circumference, right? So a circumference would be 2 pi times whatever the radius is, which is rho, right? That would be the circumference. So if I just want a piece of that, if I just want this highlighted region from E naught to E1, I take the rho and I multiply by delta phi. Does that make sense? So that's just that arc length. That's all I've got, is that arc length. And, you know, we're going to make some approximations. We're going to say it's not really an arc, but it's a line. Okay, why? Because, well, it's a small angle. Small angle rotation, so, you know, arc versus line, the same thing. Then, what do? We say, oh, well, hey, this is exciting. Well, maybe not. This is that right here, that highlighted line I now have put here at the top of this triangle. And this triangle is the triangle that's carving out, okay, what's happening between H1, E naught, and E1. Okay, just like that. And it has some delta Z, right? That's the delta Z. The delta I said was rho delta phi. And voila. We have another angle, right? Not the delta phi, but we have another angle, and that we call gamma, and that's the shear strain. Is that complicated? Maybe a little bit. Okay. But you can understand it. You can understand it. Could you create this from thin air? No. We had hundreds of years, thousands of years of people thinking of things, right? So anyway, shear strain, okay, can be thought of as this rho delta phi over the delta z, right? Rho delta phi over delta z, right? Remember, because we said that was the tangent. The tangent of this dude is delta over delta z. Okay? But it's small angle approximation, so we're just going to say the gamma is approximately rho delta phi over delta z. But delta z has some thickness to it, and so what we're going to say is that we take the limit of this ratio as delta z goes to 0. And so these deltas, instead of them being deltas here, we're going to put d's, and this becomes a derivative. Okay? So as I shrink the thickness, as I go from Chicago pizza to New York pizza, right, I'm taking a derivative. And that's rho d phi dz. That, folks, is the shear strain due to an amount of rotation, okay? Or a slope of rotation, okay? Remember, right? What was phi at the very beginning in the previous slide? Phi was this idea of, whoops, nope, don't do that. Phi was essentially a concept of how much does the whole shaft rotate, okay, as a function of where you are along the shaft. Now we've said the derivative of that rotation, okay, with respect to the length that where we are, you know, as we're coming out of the shaft, that is d phi dz. Okay, so shear strain in a circular shaft is this, rho d phi dz. And shear strain is dependent on rho, okay? And if we have a constant internal Tz, then gamma is independent of z. Okay, shear strain gamma is a maximum when rho equals c. Okay, remember rho is defining different circles. Define is the radius of these different circles within the circular cross section of the shaft. It can't get larger than c to have any meaning. Okay, there's no shear strain in the air around, for our intents and purposes. There's no shear strain in the air around the cylinder. Okay. There's a linear gradient, though, what this means, right? So rho d phi dc. So if you're at a given location and you have the slope, then if rho is equal to 0, then your shear strain is equal to 0. If rho is equal to c, it's going to be not that. Okay, it's going to be c times d phi dz. All right? And we can say that the max, if we know what the maximum shear strain is, which is happening at the outer surface. Okay, so now maximum shear strain is at the outer surface. Then if I know where I am relative to that outer surface with rho, and I know the c, the radius of the cylinder, then I can figure out where my gamma, my local gamma is. So I can figure out where that gamma is anywhere along a rho. Okay? So at rho equals c, gamma is the maximum. At rho equals 0, gamma is 0. And at rho over, or at rho, like somewhere in between, it's rho over c times whatever that maximum shear strain would have been at the outskirts. All right, so a couple of things. Angle of rotation along a shaft. We also know that the angle of rotation along a shaft is proportional, right, to the where it is z. So this is like now going back to the length of the shaft, right? We can figure out that it's going to be dependent on how far along you are, okay? And the I'm going to have to delay. Okay, I came late, so we're going to have to pick this up. Torsion formula is pretty important, extremely important. We'll pick that up on Tuesday, and I will delay. So you have stuff due on Tuesday after the exam, but I will delay the due date for the questions that have to do with torsion. Okay. Monday, I will be on time. Right? Okay, I will. And let's make sure that you're on time. And let's make sure that you have a sheet, front and back, with whatever you want written on it. Write down previous exam questions, whatever you like. Okay? Try not to use a microscope. Please no copy and paste. Alright? Please no copy and paste. Alright? So it needs to be handwritten. It can be handwritten on your tablet and then printed. But I know what a copy and pasted graph looks like. Right? I know what copy and pasted formulas look like. Okay? Yeah, sure. If you want to like use Microsoft Word to make a few formulas look, I'm not gonna whatever, you know. But just write it. It's just write. Just write handwritten stuff, and then you've got this nice note that you can take with you for your career. I have a folder in the office somewhere with like all my formula sheets that I was allowed to take. Honestly, I don't use them because there's the internet. But you know, if you ever want to like be nostalgic and be like, I remember that. I remember when that teacher told me my handwriting was too small for my formula sheet. Yeah. So like those kinds of things. All right. But I'll see you on Monday. All right. Have a good weekend.